Hey everyone, today we're going to take a look at chemical reactions. Chemical reactions are some kind of process that occurs, and they can often be described by using a chemical equation that shows you the exact kind of change that's occurring. In a chemical equation, we essentially have two sides to it, the reactants on the left side and the products on the right side. Your reactants are those substances that are at the start of the change, and the products are those being formed at the end of the change. In a chemical equation, we could show many bits of information, some of which including the states of matter, any sort of temperature or pressure conditions, along with the use of catalysts. We use symbols to indicate these very specific conditions, whereas for states of matter, we would just label it with either an SLG for solid, liquid, or gas, an AQ should it be dissolved in water, and we can even indicate if a reaction is reversible or not through the use of a one-sided or a double-sided arrow. But all chemical equations essentially kind of start the same and tell you the same information, what's beginning the process and what are you getting out of it. Now in a chemical equation, we can represent those in different ways. One way is through what's called a word equation. A word equation is essentially just a statement or a sentence that's describing the actual process occurring. So we wouldn't use any symbols here, we just use our words. So for example, upon heating, sodium chloride decomposes to form solid sodium and chlorine gas. So that here is describing to you in a statement exactly what process is occurring where sodium chloride is being decomposed into sodium and chlorine gas. Should we be writing with symbols, we typically start a chemical equation in what's called a skeletal form, where it's an unbalanced equation, merely showing you the different substances involved and any kind of specific information required. Now, a skeletal equation is not the correct representation because although it tells you exactly what's involved, it is not keeping track of one very important piece of information, and that is the law of conservation of mass. We know in any chemical processes that matter cannot be created or destroyed. So even during a chemical reaction, matter is not created nor destroyed, and our equation has to reflect that. So we must turn a skeletal equation into a balanced equation in order to uphold this law. A balanced equation just uses coefficients in order to represent the quantity of each substance involved in the reaction to ensure that the law of conservation of mass is held. Essentially, a balanced equation is making sure that atoms are only rearranging and not forming or disappearing anywhere. And to balance the equation, all we must do is just adjust these coefficients in the front of these different substances. Let's take a look at why exactly we need to balance an equation. Let's say we're looking at the formula for making water. We have hydrogen and oxygen combining together to make H2O. Now, if you notice here, we're starting with 2 hydrogen atoms, 2 oxygen atoms, and then all of a sudden, we're only left with a single oxygen atom. What happened to that last one? Well, this would imply that one atom of oxygen has been destroyed, but that's not possible. So this is the incorrect way to show the reaction to form water. Instead, a balanced equation would uphold that, and we can see that the number of atoms are conserved. That instead of a single molecule of hydrogen, we actually require 2 of them, 1 molecule of oxygen, and this produces 2 molecules of water. So we can see here that the number of atoms is constant on both sides. 4 atoms of hydrogen, 2 atoms of oxygen, and in the end, even though they're now in a different form, we still have the same number of atoms of each element. And that's what it truly means to balance an equation. These coefficients, like the 2 in front of the hydrogen and the 2 in front of the water, are merely telling you how many of each substance there are. So how exactly do you balance an equation? Well, balancing an equation is essentially like a puzzle. There's a few methods to go on about it, but in the end, we're just trying to make sure that both sides of the equation are equal. So here are some beginner steps for how to balance an equation and give you kind of a mindset of where to begin. We usually want to start by balancing the metals in the equation, ensuring that the number of atoms of the metal elements are equal on both sides. Then we want to balance the nonmetals. Here we want to be careful to leave any diatomic elements as last. Then once we're done, we just want to double check to make sure that the number of atoms are equal on both sides. Now, early on, with easier balancing equations, we can take a look at finding lowest common multiples in order to ensure this. But as the equations get a little bit more complicated, different methods and experience is going to be needed. So let's look at a few examples. Let's balance the following chemical equation, where we have NH3 decomposing into N2 and H2. We always want to start off by taking our atom inventory, which is just keeping track of how many atoms of each element are on both sides of the reaction. So what I like to do here is underneath the arrow, I like to list out the things that I'm balancing. So in this case, I am balancing the nitrogens and the hydrogens. So I'm going to take my inventory, aka I'm going to take a count of how many atoms I already have initially of each element. So on the reactant side, we have 1 atom of nitrogen, and on the product side, we have 2. For hydrogen, we have 3 atoms on the reactant side and 2 on the product side. As you can see, we don't have the same number of atoms right now for either element on both sides of the reaction. So this is going to require us to balance it. So these coefficients behave just like they would in math. They're essentially multiplying everything that's next to them. So our initial approach here is to look for a lowest common multiple between both sides. So between 1 and 2 for nitrogen, the lowest common multiple would be 2. So here I want to make both sides equal to 2, and the way to do that is to take 1 and multiply this by 2. And now this 2 I'm going to represent in a different color because this is my multiplier. By multiplying by 2, essentially I am making the coefficient in front of NH3 2. This is how I'm going to multiply the amount of nitrogens by 2. However, if you notice in this case, the hydrogen is also bonded to the nitrogen. So on the reactant side, I'm multiplying not only the amount of nitrogens by 2, but also the amount of hydrogens. So I have to make sure to keep track of this and know that this hydrogen is also going to be multiplied by 2 because they're bonded together. So afterwards, we get 1 times 2, which is 2 nitrogens, and then 2 times 3, which is 6 hydrogens. But right now, the number of nitrogens I have are equal, 2 and 2. So now I'm going to move on to the hydrogens. After that 1 change to the nitrogen, my hydrogen count is now 6 on the reactant side, 2 on the product side. Once again, I want to identify what is the lowest common multiple between the two. So between 2 and 6, the lowest common multiple is 6. So in order to get the 6, I'm going to take 2 and multiply by 3. This means in front of the hydrogen, I will place a 3. So then we get 2 times 3. This is now 6. In this case, because the nitrogen and the hydrogen are separate and not bonded together, this coefficient of 3 is only affecting the hydrogen and not the nitrogen. So now when I take a look, I have 2 nitrogens on both sides, 6 hydrogens on both sides. So now this equation is balanced because I have the same number of atoms on both sides. So my final balanced equation would be 2NH3 forms 1 molecule of nitrogen and 3 molecules of hydrogen. These coefficients just tell us how many of each of these substances are involved here in order to balance this equation. Now let's look at a few more practical examples. Let's say we have KClO3, potassium chlorate, and it's going to decompose into potassium chloride and oxygen. Once again, start off by taking our inventory, K, Cl, and O. So by starting off, I have 1 potassium on each side, 1 chlorine on each side, 3 oxygens on the left, 2 on the right. So in this case, my potassiums and my chlorines are already balanced. So now it's a matter of balancing my oxygens. For my oxygens, I have 3 and 2. So I want to look at what is the lowest common multiple. So between 3 and 2, the lowest common multiple is 6. So then, in order to go from 3 to 6, I must multiply by 2. So I'm going to identify the oxygen. Now the oxygen here is bonded in this potassium chlorate compound. So this 2 must go in front of the compound, not in the middle of it. Doing so will also multiply the chlorine by 2 and the potassium. So now I have 6 oxygens, 2 chlorines, 2 potassiums. Doing so has caused our potassium and our chlorine to no longer be balanced. And that's okay. Sometimes this is going to happen, but it all works out in the end because we're going to adjust now. So now I have 2 potassiums on the left and only 1 on the right. So lowest common multiple between 1 and 2 is 2. I will multiply this by 2, which means placing a coefficient in front of KCl. That will cause this chlorine to get multiplied by 2 as well. So then we get 1 times 2 is 2, 2 times 2 is 2. So now we fixed our problem. Our potassiums and our chlorine originally balanced at 1 and 1. Now they are rebalanced at 2 and 2. Finally, let's go finish up with this oxygen. So again, we're looking at the lowest common multiple of 6. I've already taken care of the reactant side, and now it's time for the product side. In order to get to 6, we get 2 times 3. That would be 6. So then our coefficient for the oxygen is 3. We can see that both sides are balanced now at a count of 2, 2, and 6 for each of these elements. So our final balanced equation looks like 2, 2, 3. So now let's do one more, but this time we're going to toss in a polyatomic ion. So we have iron 3 chloride and sodium hydroxide reacting to form iron 3 hydroxide and sodium chloride. So again, we start off with our atom inventory. So we have iron, and I like to list all the metals first, so that's kind of go in that order. Sodium, chlorine. Now for this last one, I can definitely separate it into oxygen and hydrogen. But if I'm noticing here, I have a hydroxide polyatomic here and a hydroxide polyatomic here. So while I could definitely separate this into O and H, I often like to keep the polyatomics grouped up together since they appear on both sides. So I will keep OH hydroxide together and count that as one whole group. So now for my count, I have 1 iron on each side, 1 sodium on each side, 3 chlorines on the left, 1 on the right, 1 hydroxide. So this whole hydroxide polyatomic ion, I have 1 of those on the left-hand side, but 3 of them on the right. So that's how I'm going to take my inventory for this one. So iron and sodium are already balanced. Now it's time for chlorine. I have 3 chlorine on the left, 1 on the right. Lowest common multiple is going to be 3. So multiply by 3. I'll put a 3 in front of the NaCl. That will cause Na to multiply by 3. So Na has 3, chlorine has 3. Now my sodiums are no longer balanced. I want to go ahead and take care of that right now. So I have 3 sodiums on the right, 1 on the left. I must multiply by the right by 3 to balance that out. 3 will go in front of the NaOH, giving me 3 sodiums. I have a hydroxide attached to that. That's also going to triple it, giving me 3 hydroxides. So my sodium got thrown off because of the chlorine. But readjusting the sodium actually fixed what I was going to do with the hydroxide, and now that's balanced as well. Both sides are equal, and now we're finished. Our balanced equation gives us the coefficients of 1, 3, 1, 3. Balancing sometimes can be a real pain. This is where experience and practice comes in. We can handle a bunch of situations, but early on, for simple balancing equations, this method will work where you just want to look at the lowest common multiple and just adjust as you go. As they get more difficult, they become a little bit more complicated and require you to try different methods. It's not always that straightforward, but that's where practice is going to come in, and the experience of just doing these over and over again will eventually help lead to handle any kind of balancing. But for now, this is how we balance equations, trying to uphold the law of conservation of matter.